Hello, everybody. In this video, we're going to talk about mixing of covalent compounds. Okay, so when it comes to mixing of covalent compounds, I'm going to try to summarize everything that we need to know about mixing of covalent compounds here. So, the first thing that should come to our mind is if two things mix, okay, they should be able to interact with each other, okay? So if we have two substances, say A and B, okay? So if we have A and B, I'm gonna have probably something different for them. So let's say that our A's circles, okay, and then our B's are triangles, okay, and this is our unmixed state, okay. So A and B are not mixed, or they are in the unmixed state. Okay, this is the unmixed state. Okay, and then when they interact with each other, okay, when they interact, if they mix with each other, then you're going to get the mixed state. In the mixed state, you're going to have both A and B. Okay, so here are some of our B molecules, if I may. Okay, and then in between we have the A molecules. Okay, and this is how we characterize our mixed state. Okay, then again, so this is just to visualize what is happening here. So we have the unmixed state and the mixed state. And if two things mix, the idea is they have to be able to interact with each other. Okay, because if they cannot interact with each other, if they do not have similar type interactions, then they are most likely to stick with the same type of atoms or same types of molecules rather than getting mixed with each other. Okay, so the mantra here is A and B mixed, A plus B mixed. Okay, mantra for predicting solubility or the mixing is let's write that. The mantra to predict the solubility, to predict the solubility, we're gonna use this mantra: like interacts with like. Okay, now just to make sure that we understand what is meant by this, so say that we have water. Okay, so say that we have water, and then we have say ethanol. Okay, I'm gonna draw ethanol like this. Okay, and then if you think about water is a polar molecule with hydrogen covalently bonded to oxygen. Therefore, we can have dispersion because anything has dispersion forces, and it's going to have dipole forces. Okay, we call this DD, and also it's going to have hydrogen bonding forces. Okay, HP. So we have all three types of interactions between water molecules. And if you look at the ethanol molecules, Okay, ethanol molecule also going to have dispersion forces, and it's going to have dipole forces because it's a polar molecule. All right, you just have a dipole moment, net dipole moment of the molecule in both cases. Okay, and also it's going to have hydrogen bonding forces. No, I need to have a different color, black. Hydrogen bonding forces. Why? Because you have hydrogen covalent bonded to oxygen there as well. There we can have hydrogen bonding interactions. So you see that they both have similar types of intermolecular forces. Therefore, if you put them together, okay, I say this in class that if they go to a party, they are more likely to interact with each other. Okay, so therefore we can predict that these are going to mix. Okay, so prediction is they will mix. And you know what? Let me draw it here. Okay. We can predict them to mix. We can predict them to mix with each other. Because they have like interactions. All right, let's take another example. Let's stick with water for a second because we talk a lot about water when it comes to mixing. We talk about the water solubility, which means the same thing. Okay, water and something like oil, or maybe something that is totally, that is considered non-polar, like this molecule over here. Okay, so if you write the interactions we have, water has dispersion, dipole, and hydrogen bonding. And then this molecule on the other, on the right-hand side, only have dispersion forces because it's a non-polar molecule. Now, here's the thing: if you look at this, because they do not have like interactions, okay, the water will rather interact with other water molecules rather than interacting with this molecule over here. This is 1, 2, 3, 4, 5, 6, 7. So this is heptane. It's a normal heptane. In case you want to give it a name, normal heptane. Oh, heptane. Okay. So and then heptane molecules likewise, right? Like heptane molecules do not have dipole interactions, so hydrogen bonding interactions. Okay, they cannot. So these heptane molecules rather interact with other heptane molecules than interacting with water molecules. Okay, as a result of that, they wouldn't mix. Okay, so we can say that we can predict them not to mix with each other. Due to the lack of like interactions. Okay, so that is how we use solubility. That's how we use this mantra: like interacts with like interact with like, to predict whether two things mix or not. Okay. Yeah, that's that. And then that is about prediction. Okay, and we want to talk about like explanation as well, solubility explanation as well. So let me see if I can have a new whiteboard. Now, mixing is a process. Okay, just like anything, any other process. Okay, we have the initial state, Our initial state of mixing is the unmixed state. Unmixed state, okay? And then the final state of the process of mixing is the mixed state, okay? And then we can think about the likelihood of two things to mix in terms of potential energy and the number of configurations, okay? So this is our mixing process. Now let's think about this, okay? Now we know that the mixed state has more configurations than the unmixed state if they mix, okay? So if two things mix, then the mixed state must have a higher number of, we can imagine it to have a higher number of configurations, okay? Now, again, because we're talking about the potential energy and number of configurations here, so let's see, let's write this down. So potential energy and the number of configurations, okay? Potential energy, okay, which is related to interaction strength. Interaction strength, and then we have the number of configurations. Okay, will determine whether two things mix or not, okay? So now let's look at the different possibilities, all right? So the possibilities are, we use PEC diagrams to determine or depict the probabilities here, or possibilities here, okay? Let's have our potential energy on the y-axis and the number of configurations on the x-axis. Now, say that our mixed state has a lower potential energy and a higher number of configurations than the unmixed state. If we have a situation like this, okay, we see that the mixed state is favored by the potential energy. Why? It has a lower potential energy, meaning we have stronger interactions in the mixed state, and also it has a higher number of configurations. Therefore, the mixed state is favored by the number of configurations as well. If this is our situation, this is going to be soluble or miscible at all temperatures. There's no doubt about that. Always mixing. Okay, we can write soluble at all temperatures. If this is a situation, it's going to be soluble or miscible. Soluble or miscible at all temperatures. If we have this situation, why? Because the mixed state is favored by both the potential energy and the number of configurations. And then what we can think about is, where do we have strong interactions, okay? Or intermolecular forces, IMF strength. Okay, just to summarize everything in one place. Mixed state will have strong interactions than the unmixed state. How do we know that? Mixed state has a lower potential energy, meaning it has stronger attractive interactions, because the stronger the attractive interactions, the lower the potential energy. And then we can also think about the effect of temperature. Let's stick with increase in temperature. We can think about decrease in temperature as well, because it's the other way around. Increasing temperature will decrease the solubility. Okay, why? Increasing temperature or high temperatures favor the state with high potential energy, which in this case, the unmixed state. Okay, therefore, increasing temperature will start favoring the unmixed state rather than the mixed state. Therefore, it's going to decrease the solubility or decrease the mixing when you increase the temperature. Okay, so that is one. And then let's do another one. Let's do the other obvious thing. Let's say that we have this situation, configurations. So say that we have the mixed state over here and the unmixed state over here. Now, if you have this situation where mixed state has a higher potential energy and a lower number of configurations compared to the unmixed state, the unmixed state is always favored. Okay. In other words, this is insoluble, always insoluble or immiscible at all temperatures. If you have this situation over here, and then IMF strength okay. Because unmixed state has a lower potential energy, unmixed state has stronger intermolecular forces than the mixed state. Okay, interactions between, let's say the A and B. Okay, as in our previous example, interactions between A and B are weaker than the interactions between A and B and B. That's what it means, right? And then the effect of increasing temperature. If we increase the temperature, the solubility will increase. Solubility will slightly increase. Solubility increases solubility. Solubility. Actually, I would like to have the arrow on the other side. Solubility increases. Why? If you increase the temperature, that's going to favor the state with high potential energy. Therefore, it's going to start favoring the mixed state. But remember, if we have this PEC diagram over here, okay, it will never be soluble. Okay, it will slightly make it more soluble than before, but you will have more insolubility compared to the solubility. More of the unmixed state compared to the mixed state at any given temperature. Okay, so those are the two obvious things that we can think of. And then let's take a look at this. Okay, I think I'm going to draw one over here. It would be nice if we can draw two, but let's see if we can draw two of them, because it will be easy to see them for the comparison. Okay, say that we have this situation, potential energy and number of configurations. Mixed state over here and the unmixed state over here. Okay, if you have this situation, all right, this is going to be, I mean, simply we can imagine the potential energy does not favor the mixed state, but the number of configurations favor the mixed state. Okay, because number of configurations wise, mixed state has a higher number of configurations than the unmixed state, but the potential energy wise, unmixed state has a lower potential energy than the mixed state, meaning the unmixed state is favored by the potential energy. Now, if this is the situation, this is going to be soluble only at high temperatures. Okay, that's going to be the correct way of putting it. Soluble only at high temperatures. Okay, now because there's something else we need to add here. Now, because you have a higher number of configurations in the mixed state, okay, we know that number of configurations favor the mixed state. Therefore, anything that has any system that has a higher number of configurations in the mixed state is considered as generally soluble. okay? Generally soluble. Generally soluble. Considered as generally soluble. Generally soluble. Why? Because mixed state has a higher number of configuration, higher number of configurations. Okay, now the others are not that complex when it comes to IMF strength. All right, which is governed by the potential energy. So because unmixed state has a lower potential energy, unmixed state will have stronger intermolecular forces than the mixed state. And then the effect of temperature, increasing temperature will obviously increase the solubility. Solubility will be increased. Okay, let's do one other thing over here. And then we're almost done. Potential energy, number of configurations. Let's swap these. So let's say that we have the mixed state over here and the unmixed state over here. Okay, if this is the case, the mixed state is favored by the potential energy, but mixed state is not favored by the number of configurations. Okay, if you have this situation, the solubility depends on the temperature one more time. We can say that this is going to be soluble only at low temperatures. Soluble only at low temperatures. Okay, why? Low temperature mixed state has a lower potential energy, therefore lowering the temperature will favor the mixed state. Okay, but because the mixed state has a lower number of configurations, all right, this is considered as generally insoluble. Generally insoluble because M has a lower number of configurations. Okay, we should just to make it clear. Okay, and then the others are straightforward. IMF strength, IMF strength. The mixed state will have stronger intermolecular forces than the unmixed state. Why? It has a lower potential energy. And then increasing temperature will decrease the solubility. Solubility will decrease when you increase the temperature. Why? Increasing temperature or high temperatures will favor the state with high potential energy, which is the unmixed state here. Therefore, increasing temperature will decrease the solubility. All right, just for the completion, I'm going to introduce you to two more possibilities of PEC diagrams. Okay, then we're done. And it goes like this. Let's say that we have potential energy and number of configurations. Let's say that we have this situation over here, unmixed and mixed. Okay, now if we have this situation, we see that the potential energy does not have preference for unmixed or the mixed. But the number of configurations wise, you have a higher number of configurations in the mixed state. Okay, as a result of that, this is considered as generally soluble. Okay, generally soluble or generally miscible or generally mixing. Okay, why? Because the mixed state has a higher number of configurations. Okay, IMF strength, IMF strength will be comparable. So the unmixed and mixed will have comparable intermolecular force strength. And then increase in temperature or decrease in temperature for that matter will not affect the solubility. Okay, why? Because none of them is preferred by the potential energy. Therefore, increasing or decreasing temperature will not have an effect on the solubility. Okay, and lastly, we can have this situation over here, right? Mixed state over here and the unmixed state over here. Number of configurations. If we have this situation, this is considered as generally insoluble. Okay, generally insoluble. Okay, why? Unmixed state has a higher number of configurations than the mixed state, or mixed state has a lower number of configurations than the unmixed state. Same thing. Generally insoluble. And then IMF strength again. Okay, they're comparable. And then the increasing or decreasing the temperature will not affect the solubility. Okay, there you go. So that summarizes all the possibilities when it comes to mixing. Okay, so just to summarize, okay, mixing of covalent compounds. Okay, to predict, we look at the interactions. Like interacts with like is the mantra. If you have like interactions, they are more likely to mix with each other. And if they have different interactions, like water and normal heptane, then they are less likely to mix with each other. That's how we can predict the solubility. And then when it comes to the process of mixing, which is governed by the potential energy and the number of configurations, we can have six possible situations. Mixed state can be always favored if you have mixed state in this quadrant over here in the PEC diagram. Okay. And then the other way around, if the mixed state is at the it has a higher potential energy and a lower number of configurations, it's going to be always insoluble. If the mixed state has a higher potential energy and higher number of configurations, it's going to be soluble only at high temperatures, but it is considered as generally soluble because mixed state has a higher number of configurations. And then if the mixed state has a lower potential energy but lower number of configurations, then it's going to be soluble only at lower temperatures, and it is considered as generally insoluble because the mixed state has a lower number of configurations. Okay. And then lastly, we talked about what happens if they both are at the same level like this. Okay, if we have the mixed state at a higher number of configurations, then it's generally soluble. If we have the mixed state at a lower number of configurations, it's generally insoluble. One more time. And then IMF strength and the temperature effect is also listed for all 6 cases here. All right, I hope this helps to summarize or recapitulate mixing, the process of mixing for covalent compounds. I'll see you guys in another video where we talk about the mixing or solubility of ionic compounds. All right, bye everybody.